I want to start this video by explaining a little bit more clearly what is the difference between an insulator and a conductor. Okay, so not all atoms are created equally. Depending upon where you are in the periodic table, there is going to be a different amount at which the valence electrons are kind of bound to the atom, right? How much they're attracted to the nucleus and how free they are to move throughout the material. Okay, so when we're talking about electricity traveling through an object, please remember that it's the valence electrons that are moving. Okay, and so if those valence electrons are bound much more tightly to the atom, then you have an insulator. They're not free to move as like a sea of electrons throughout the material. However, certain materials, especially metals, have a situation where the valence electrons are more free to flow, okay? And so as this slide says, in insulators, the electrons are too tightly bound to their atoms to flow naturally in a circuit. However, in a conductor, the valence electrons are much more loosely bound and easily move under the influence of a voltage. Okay, so really this just comes down to certain electrochemical properties of the material based on where you are in the periodic table, and it just so happens that metals tend to have their valence electrons less bound, and thus they can conduct electricity. Okay, I hope that helps clarify why some things are insulators and some things are conductors. It's also extremely important to clarify what are the masses and the charges of protons and electrons, because for the rest of the semester, we're going to be using these tons, okay? So you may have heard protons are much heavier than electrons by 4 orders of magnitude, actually, okay? So a proton is 1.67 times 10 to the minus 27 kilograms. Obviously, that's tiny, but it's still much, much heavier than an electron, which is 9.11 times 10 to the minus 31 kilograms, okay? So the electrons barely contribute to the overall mass of an atom, and you'll notice that the atomic mass of an atom is actually measured in terms of the protons and neutrons, because they actually are the ones that contribute to the mass, unlike the electrons. And so a proton has a charge of plus E, where E is the standard charge of a proton and electron, which is 1.6 times 10 to the minus 19 coulombs, all right? Coulombs being the unit of charge for charge. And so for an electron, the charge is negative E, no big surprise. We all know that electrons are negative, but that means that the charge on an electron is negative 1.6 times 10 to the minus 19 coulombs, okay? And so let's look at our first problem of the week. So one area where this really matters is signal propagation in neurons, right? Everything that I'm doing, everything that I'm saying, moving my arms and all this business that's happening is happening because in my head, my brain, right, there are a whole bunch of neurons that are constantly accepting and transmitting ions, positive and negative charges. These are sodium and potassium in particular, okay? So you guys have maybe heard that you have along these axons, like massive amounts of sodium or potassium ions that travel through, right? So I'll just go ahead and read. Neurons are components of the nervous system of the body that transmit signals as electrical impulses travel along their length. And we're going to look at this more closely in future lessons. These impulses propagate when charge suddenly rushes into and then out of a part of the neuron called the axon. Measurements have shown that during the inflow part of this cycle, approximately 5.6 times 10 to the 11 sodium ions per meter, each with a charge of plus E, because they're just plus 1 ions, enter the atom. How many coulombs of charge enter a 1.5 centimeter length of the axon during this process? So we know approximately how many ions per meter, right? But we want to know exactly how many coulombs of charge that is. Like, how much charge is that really? All right. So here's the deal. We first know that it is 5.6 times 10 to the 11 sodium ions per meter. All right. But these axons are relatively small. We're not talking about a full meter here. We are talking about, let's say, a 1.5 centimeter length of an axon, right? Which is 0.0015 meters, right? So to find out how many actual sodium ions, I need to multiply that by 0.0015 meters, right? Because that's, if this is the amount of sodium atoms per meter, and that's only the amount of meters that I have, we're not going to get the full 5.6 times 10 to the 11. Instead, we are going to get 8.4 times 10 to the 9 sodium atoms being flushed into that axon, okay? That's how many, not the full amount, only this much because the axon isn't a full meter in length, right? Okay, so if you agree with me there, now that we know the number of sodium ions and we know how much charge there is per ion, I can tell you how many coulombs of charge enter that axon, right? And you simply do that by saying, well, if I have 8.4 times 10 to the 9 sodium ions, I would just need to multiply that by 1.6 times 10 to the minus 19 coulombs for every sodium atom, right? That obviously cancels out. And when I multiply those guys, I get 1.34 times 10 to the minus 9 coulombs. And again, if you ever catch me getting something wrong, I've made mistakes before, feel free to shoot me an email, but I'm pretty sure that's the right answer. In that neuron, in that axon, there is a flush of 1.34 times 10 to the minus 9 coulombs, which is different than the number of ions, okay? In general, we care more about the amount of charge than we do the number of ions. And we'll see why later in the course, okay? This brings up an interesting question. Normally, when we think of a unit, we think of, one of that unit being a relatively small thing, right? Like 1 centimeter per second is relatively small. 1 pound is relatively small, right? How big really is a coulomb? Is a coulomb a big unit or a small unit? Let's see. Let's answer the question, how many electrons would there be in a 1 kilogram bag of charge? So let's say that here I'm holding a 1 coulomb, sorry, not 1 kilogram, but 1 coulomb. I'm holding a 1 coulomb bag of electrons. I have all these little electrons in here, and they add up to 1 coulomb. Okay, all right, how would I do this? It's actually quite simple. I know that for each electron, there is 1.6 times 10 to the minus 19 coulombs, okay? So I would just have to divide 1 by 1.6 times 10 to the minus 19, 1 coulomb by 1.6 times 10 to the minus 19 coulombs per electron to find out how many electrons that would be, okay? All right, so just do it. 1 divided by 1.6 times 10 to the minus 19 gives you the astronomical number of 6.25 times 10 to the 18 electrons. That's a lot of electrons, okay? Turns out a coulomb is actually a pretty unusually large charge. We rarely talk about charges this big because, that's 6.25 times 10 to the 18. It's more than a billion, it's more than a trillion, it's off the charts. Off the top of my head, I actually don't even remember what times 10 to the 18 is. And so many times when we talk about charges in this course, we're going to talk about nanocoulombs or microcoulombs because, as you can see, this is quite a lot of charge. Okay? With that said, in the next video, we're going to actually start to quantify how much force in newtons, right? These are forces. So we're talking about a force in newtons. How much force can you actually experience between two charges? And how do we calculate that? And what should it depend on? This is called Coulomb's law. And in the next several slides, we will dive into exactly what Coulomb's law is and how to calculate the force between charges.